It's all Google's fault. When they published the data for their new Willow chip, their press release contains this controversial little sentence. It lends credence to the notion that quantum computation occurs in many parallel universes, in line with the idea that we live in a multiverse, a prediction first made by David Deutsch. And this particular notion has become somewhat widespread in popular science recently. For example, this is Michio Kaku's version of it.
That's what gives quantum computers their power. They compute on not just one universe, but an infinite number of parallel universes.
The Google announcement mentioned Oxford professor David Deutsch, who is both one of the fathers of quantum computing and also a staunch believer in the many worlds interpretation of quantum theory. So I think we need to talk about all of that. The many worlds interpretation of quantum mechanics is based on Hugh Everett's PhD thesis named The Relative State Formulation of Quantum Mechanics and was published way back in 1957. It was born out of discontent with the standard or Copenhagen interpretation of quantum mechanics from the 1930s. But why? Well, the big difference is how measurement is explained. In the Copenhagen interpretation, measurement is an interaction of the quantum world with the classical world. In the quantum world, the state of a system is described by a wave function, which is collapsed by measuring it, from a superposition of all possible results to just a single real result. The probability for getting a result can be calculated from the wave function. In many worlds, we also have the wave function, but all measurement results are considered to actually happen, just in different branches of the universe. The interaction of the wave function with the measurement apparatus causes decoherence, and this causes branching, so a complete separation of the previous superposition. Actually identifying these branches with different worlds or parallel universes is a very modern perspective that was introduced decades later. Let's be clear about one thing, which is a common misunderstanding. Many worlds does not say that each part of any superposition exists in a parallel universe. Only a measurement triggers decoherence, and decoherence triggers branching. Everything in a superposition is still part of our one universe, and may still end up as our measurement result later. What this achieves is explaining part of the measurement problem, namely the collapse of the wave function, or at least explaining it away to different universes that are conveniently undetectable. This also allows us to explain measurement by using the Schrödinger equation and does not require us to shoehorn in something additional like the collapse of the wave function. While this may sound like an esoteric detail to you, this is actually the main draw for physicists of the many worlds interpretation. And there are many more things to say about many worlds, but this is all we need here for this video. Personally, I would describe my position towards many worlds as both disinterested and somewhat uninterested. That means, firstly, I try to be very neutral about it and take it seriously. So even if I'm not won over by many worlds, I will gladly admit it is a viable interpretation of quantum mechanics that serious people may hold. And it might even be true, whatever that means. And secondly, I just don't really care too much about it. It makes all the same predictions as regular quantum mechanics, so it does not really bring any new physics to the table. Very much like the pilot wave interpretation, it seems to be much more attractive to philosophers and laymen than actual physicists. Be that as it may, the only important point here is how many world explains measurement. Namely, a superposition of possible outcomes exists in one world. Then decoherence branches this up into separate worlds where each outcome is measured and the observer in each branch only sees the respective result of this branch. What does all of this have to do with quantum computing? Many quantum algorithms are built around the fact that quantum operations on a superposition of states will work on the entire superposition at once, so on all components. And again, let's be careful here, because that's another popular misconception. That does not mean that quantum computers work by trying out all the different answers at once. Because there's a catch. The catch is that, yes, quantum computers can run a computation on a superposition of all inputs at the same time, but as soon as you read an output, the superposition will collapse and only return one random result. Or if you prefer, one version of you will find yourself in one universe where this result was measured. So simply running a computation on a superposition of all possible inputs alone will not achieve anything. What you need to do is then find a smart way so that all these parts of the superposition will add up to amplify the desired outcomes and will weaken or cancel out all undesired outcomes. So that when a measurement is made, it will deliver the desired outcome with high probability. It is of course very difficult to figure out an algorithm which achieves exactly that. And this is exactly the reason why quantum computers are only useful for a very small set of very specific tasks. For example, the famous Shor algorithm is able to factorize a large number into its prime number components. This sounds like it would only be useful for a small number of mathematicians, but actually this means it can crack the most common encryption methods of today. And this is where David Deutsch argues, when Shor's algorithm has factorized a number using 10 to the 500 times the computational resources that can be seen to be present, where was the number factorized? There are only about 10 to the 80 atoms in the entire visible universe. So, how and where was the computation performed? But there is a big inconsistency here. Such arguments invoke many worlds, but do not adhere to what many worlds actually says. Superpositions, like the one used in Shor's algorithm, do not exist in many different universes, just in one. Only the different outcomes after measurement will be in different worlds. So Deutsch overstretches what many worlds actually says, or he uses his own variation of many worlds, without acknowledging it. In this case, he will have to explain how a process can at the same time be spread out over many disjoint universes that cannot interact with each other, but also can all collaborate again to get the correct result, and then be separated again after measurement. This is a very inconsistent use of separate many worlds, so it appears that they are separate whenever we need it and then can collaborate again when we need that too. But that's just a minor side note anyway. Let's go straight to the main point. The idea that quantum computers get their power from computing in many universes inherently cannot be tested. These supposed many worlds are not accessible to us, and as long as this is the case, it's fine to speculate about them. But it's important to acknowledge that this is what we're doing here. Because it is the biggest sin of popular science to pretend that some speculative idea is proven fact. I criticize this with string theory, and I criticize this here again strongly. And again, many worlds is an opinion, and it's fine to hold it as an opinion. But dressing up this opinion as anything more is straight up dishonest, especially towards a lay audience. And it's actually damaging to the public perception of science. It gives the impression that all physics is just coming up with wacky ideas that sound awesome and then preaching them. And that physics has been completely removed from reality by now. The idea that quantum computers get their power from computing in many worlds is not even consistent with the many worlds framework. Also, it can neither be proven right nor wrong, so it is at best an interesting idea. The Google Willow chip did not change anything about this, and neither did any other discovery in quantum computing. Actually, discussions about many worlds in the quantum computing field are almost non-existent. They had to quote Deutsch because there is no one else to quote. Subscribe for more quantum computing stuff.